Hi, my name is Antonio Cervantes,
And I'm Christian Pedrigal.
and we are the activity detection system predicting steady state cardio activities based on inertial measurement data using Kerasclassifier classification models. So, what is the activity detection system? It is the application of neural networks to predict exercise or sports activities and predicting what exactly that activity is. So nowadays, machine learning can be seen in almost very many applications. However, most applications aren't really helping people or society. For example, you can look at something like targeted ads on Facebook. But there are some interesting applications that actually do help people. Uh, a professor named Max Little is a researcher from Aston University who developed a way to use machine learning to detect early signs of Parkinson's disease using smartphone motion data. This is a revolutionary because he came up with a way to use data, which is collected by our phones, which is typically done almost every day. And he applied that aspect towards an ethical and helpful application for people and medical doctors. So this was one of the main inspirations for our project because of the simplicity of the data collection and the useful and helpful application.
So, applying what we learned about machine learning to our own project, our activity detection system can currently detect 7 physical activities. First, we have walking. Second, we have stair climbing. Third, we have mountain climbing. And then we have biking and running, jump roping, and even squatting. So what kind of data do we need to collect in order to distinguish these kind of activities? We used similarly in this related work, inertial measurement unit data consisting of orientation and acceleration. So in the figure below, you can see that during a squat, you can see that there is an angular displacement at the hinge. And also on the next slide, when you run or when you sprint, you can see a linear or translational acceleration. So we're using orientation and acceleration data across all 3 axes. So a total of 6 dynamic signals were collected to learn more about these kind of activities. How did we do that? Actually, there is a really a nifty feature on MATLAB called MATLAB Mobile, which allows us to collect from the smartphone itself and send it to the cloud. Considering that my partner Antonio and I were working virtually, this was a very efficient and effective tool. When we did collect the data, it was very important to have the orientation of the smartphone in a certain way. So whenever a data was collected during a session, the orientation of the smartphone would face downwards and the screen would be towards the thigh. And as you can see, these are the default axes of rotation for the smartphone. Lastly, when we were collecting the data, it's kind of important to do some treatment so that we can extract more significant information. Several of these techniques, not all listed, included trimming, equalizing data collection times, connecting sinusoidals. You can actually see in the top figure that one restriction with collecting IMU data is that its working domain is restricted between negative 180 and 180, which is not helpful when the mean angular, the mean orientation is somewhere above 0 or maybe closer to 180. So we actually had to do some post-processing techniques. And lastly, we have low pass filters, which is very common when working with signal processing. We made sure to choose a passband that was not getting rid of the high frequency signals, but also low enough so that we can extract more relevant information. So onto our methods, I'll first talk about what kind of features we need to extract. So since performing activities, you usually have a range of motion, and these activities were repeated in a similar manner for each rep, I hope. We use sinusoidal characteristics as the activities features. So we actually have three distinct features. On the next slide, I'll be first talking about the primary frequency, I like to call it. Rather, it's actually doing the fast Fourier transform so that we can view the signals in the frequency domain. And then we're just gonna collect the maximum frequency, or we'll use the power of spectral density, which serves the same purpose. Feature number 2 involves the average peak-to-peak amplitude. Physically, this signifies the range of motion of an exercise. So let's take for a squat, for example, it has a larger range of motion. The last feature is the time derivative acceleration. So this one is not a common sinusoidal characteristic, but we wanted to explore this jerk, this time derivative acceleration, to see if we can extract any relevant features from the sinusoidal data. So considering that we have 3 features and even 3 axes, we actually had 9 features per data sample for 7 activities. So we hope that we had a lot of activities, but Antonio will explain more about how that went. As you can see, just to end off my part, there we plotted a live view of all 7 activities features. Very nicely on Jupyter Notebook. It shows variance, not variance, the how wide and spread the data are, and hopefully distinct they are from each other. So Antonio will talk about the performance and the creation of the neural networks.
Thank you, Christian. So after processing and building the data set, we began to build the neural network code. We use the scikit-learn Kerasclassifier function. The reason for using this was because using the standard methods to build a Keras neural network was not working for us, and we were getting input shape errors and other various errors. So we found that this function was really helpful. This function is a wrapper that builds a Kerasclassifier neural network as a scikit-learn function. So we used that and we built 2 neural networks. At the top is the 2-layer neural network, and below that is the 3-layer. And we did that so we could compare the differences between the 2. And at the bottom, you can see the Kerasclassifier function, which builds the actual neural network within scikit-learn. So once we had all of our base code built up, we started to test it. And in order to tune the hyperparameters of the neural networks, we developed a systematic way of changing certain parameters and testing the accuracy of the neural network using cross-validation. Each parameter was changed 1 by 1, which is indicated in the highlighted yellow sections of the table. And we recorded the accuracy for each test. So we performed about 10 tests and recorded the accuracy of each one. We did this until we found the best hyperparameters. We found that in test 9, this gave the highest accuracy of 89%, and that was for a 2-layer neural network. And then using the highest parameter or highest accuracy hyperparameters, we tested the same parameters with the 3-layer neural network, and we found that it actually had a slightly lower score of 88.84%. So moving on, we used those same hyperparameters to actually fit the data to the model using classifier.fit, which is the function seen up at the top here. A problem with only using cross-validation is that it only evaluates the neural network, but doesn't produce a trained model. So using the fit function does actually train the model. So the two graphs seen below shows the loss of the 2-layer neural network and the 3-layer. And we can see that the 2-layer has a pretty good fit, whereas the 3-layer has a little bit of overfitting, which gives some indication that maybe the extra layer that it has isn't necessary for our problem that we're solving, or we needed to tune the parameters more. So analyzing the accuracy graphs, we can see that the test accuracy is actually very low compared to what we got from cross-validation. This told us that cross-validation doesn't exactly correlate closely to the fit function or the actual trained model. However, it does give us lots of information about how the model will perform on unseen data. So in order to understand how our models will perform, we tested the model with unseen data and had it predict which activity it saw according to the features in the dataset. A common behavior that we saw was that the neural network would confuse the walking class with other classes. So for example, to the right is the confusion matrix. And this one in particular on the screen is for the 2-layer neural network. We can see that the model mostly predicted the bike through squat classes correctly. However, it got confused and incorrectly predicted walking for jump rope, run, and stair classes. And with this prediction, we got an overall accuracy of 63.9%. We then tested the same predictions and data set with the 3-layer neural network. And with this prediction test, we actually saw a slightly lower accuracy than the 2-layer neural network, which does match what the cross-validation test was saying. However, the scale of the accuracy was much lower than what the cross-validation was saying. So now moving on to our conclusions.
Thank you, Antonio. So despite having a really strong cross-validation score, as aforementioned, we did not have pretty well or ideal fit accuracies. And we concluded that the model accuracy was low due to unequal amounts of data in each class, aka an imbalanced data set. Granted that the data collectors are here before you today, only me and Antonio. So we actually had to do a lot of exercising in the past couple of weeks. But with all considerations, you can see that the walking data set had over 1,000 data objects, whereas stairs, for example, had only 91 data objects. So you can probably see why with an imbalanced data set, the walking would incorrectly predict stairs as otherwise. In the next slide, I'll be talking about future improvements that we can do. First and foremost, we would have to collect. We would probably prevent an imbalanced data set, likely, make sure that all data objects would reach a certain threshold and check that during our data collection phase, and also get more data collectors. When I was running, I would probably run a certain pattern, or when Antonio was biking, he would bike a certain way. So having not just a larger data collection data set, but also have more people performing these exercises will probably bring us more accurate or more diverse data. Also, another future improvement is to utilize more MATLAB toolboxes. During the labs here in the ME 297 class, there were a lot of useful MATLAB tools, not just for MATLAB Mobile, but other ones like the support vector machine or the wavelet analyzer in recent labs. So considering that we had a MATLAB to Python a pipeline, maybe we could have used more MATLAB toolboxes before transferring it to Python to extract features instead of hard coding it. And lastly, and in every machine learning project, there's always hyperparameter tuning. So some of the potential applications should this project come to a very successful one is that it can be used in healthcare. As aforementioned, we can use machine learning to detect Parkinson's disease. But with IMU data, we can, from this project, we can actually probably, or likely, sorry, have early detection of other neuromuscular diseases as well as just having good data to understand the gait or cadence of people walking. Very important as we always carry our smartphones in our pockets. Easy to collect data. Secondly, shown on the right, usually fitness analytics usually has a smartphone, usually have people wear smartphones and have other types of data sensors, such as sensors to collect your sweat or understand your pressure, blood pressure. But perhaps what if we had wearable technology that detects your angular or your orientation and acceleration? That would be a very insightful wearable technology that hasn't been in the market and would be a great way to add to the fitness tracker market. Other than that, thank you guys for listening, and we hope that the activity detector system will come to a very successful end as we continue to work on this project after the end of this class. Thank you so much.
Thank you.